We miss a little bit from chapter 5, and then we are going to start on the latest chapter, the final chapter, number 6. We need a couple of elements from that one as well. Yesterday we stopped when we came to this table 5.1, which you also find on the exam attachments, so you don't have to remember this, but you should know how these are constructed, or how you can sort of prove that these are correct. I did one yesterday. I think I'm going to do it again without this integral formulation, so I found another way to do it. This one, transformer and an inertance, is claimed to be the transformer squared multiplied with the inertance, sort of an equivalent inertance there. So let's see if this one is correct. You choose any causal form here. Here I take an integral form. You can do the same with differential form. It really doesn't matter. But now construct an effort like that. Then you have to be dead certain. What's the definition of a transformer? Well, a transformer, it goes something like this. If you have a flow here, then here you will find a T flow 1 as flow number 2. And here the effort 2 goes to effort 1 as T effort 2. So the T pops up there. That's sort of the definition for a transformer. If you turn the arrows the other way, it's of course flipped. So that's your decision, how you want to define your arrows. Don't do it like this. That's a bad idea. Then you have to define your own T. You can do it. It's a negative sign somewhere, but I won't recommend it. So don't do it. This is the definition of a transformer. So what do we get? Well, now I have the effort 1. So hence here I will have 1 over T P dot. Then the integral causal form for an inertance. Down here I should have only P over I. But I have 1 over T already, so this will be P over T I, right? Then I have a flow here. What then will be the flow to the left? Well, again, F1 must be F2 divided by T. So here I will then have a flow going something like flow will be P over T squared I. Now compare what you have here with an inertance. You start with P dot, and then you have the flow given with this expression. What would you have if you had just an ordinary inertance? Well, you would have P over I. But here I have a T square in addition. Hence, okay, you can call this I marked as an equivalence, which then equals T square I. That may be a little bit easier to see instead of what I did yesterday with the time integral and stuff. Any questions to that one? It's okay. So now we have proven this one. You can do the same proof doing the other causal form if you like. That's quite okay. But it's enough with one of them. The resistances here, they are rather trivial, straightforward. I'll do one of the gyrators. That one is a little bit more tricky. So let's have a look at a gyrator and an inertance. So the table here claims it should be a spring. How can a mass be a spring? It's a little weird, isn't it? Again, choose the causal form. Here I'll choose the integral form for the inertance. A gyrator, he flips the causal strokes. So if it's away from him on this side, then it has to go all the way on the other side. That's a gyrator. He changes the causal stream, you might say. So let us now start. Here I'll have a flow, say flow equals q dot. What do you get as an flow, effort on the other side? What was the definition for a gyrator? Well, if you had q dot 1, you have an effort up here that now reads g multiplied with q dot 1. And if you have a flow down here, q dot 2, you find the effort up here as g multiplied with q dot 2. So it's definitely a cross. That's the definition. So my effort here, my p dot, will now read g multiplied with q dot. And now I have an effort, okay, an inertance with the integral form. You will have p divided by I down here as the flow, as definition for an inertance. Okay, then I have a flow here. I can go and find the effort then on the other side. What will this effort be? Well, I might have to multiply with g again. Effort equals g multiplied with p over I. But this doesn't look like anything, does it? Well, what is this p over I thing? Well, I have a p dot up here. So the time integral of this equation will read g multiplied with q, only q. So I can replace the p here with g and only q divided by I. Now insert that one up here. What do you get? The effort that was equal g p over I is now equal, insert for p over I, you will have g squared q over I. That's the effort. Okay, what kind of element are we talking about now? You send in a flow, a q dot, sorry, and what effort do you get? You get this thing here, g square q divided by I. Okay, what kind of element has this property that send in a q dot and return something with just the displacement q as an effort? Yes, that is a C element, a spring. So an ordinary spring, a C element, you will have q dot down here and you'll have q over c up here. We should call him C marked then, because what will my C marked then be? Well, I have g square over I, g square over I equal to 1 over C marked, 1 over C marked. Okay, so my C mark is something with I divided by g square, as it says here. So there you have it. Hence we have proved the last the last equivalence. Also, have a look at the inertance, the causal stroke. Also worth noting. I chose the integral causal stroke here for the mass, for the inertance. And now I am told I can replace this G and I with something like this, as C marked, where C mark is now found. What about the causality? Well, now the causality actually is this one, which suits me very fine indeed, because this now is a C element still with the integral causal stroke. So the integral form sort of survives when we do this equivalence, as it should. So if you had chosen differently, started differently, if you had done something like this, G and I, and say this one was on differential causal form, like this, okay, then the gyrator, he demands the stroke then both towards him, and you can have then the equivalence would be a C marked with this stroke, still differential form, okay? So these gyrators, they are a little bit strange. I'll see if I can come up with a problem. Could be interesting to see. You have an inertance, a mass, and then you use a gyrator, and then the effect would be a spring. I can't really see this happening. I don't really believe this. I'll see if I can come up with a problem. Could be problem 1 on the exam. Okay, any questions to that one? It's okay. I won't go through any more of these. You get the idea, I think. So if I should ask you on the exam, prove one of these, then you know what to do, right? That's good. That's good. The last thing we need then from chapter 5 is mesh reductions. So that is 534, I think it is, reduction. I just call it mesh reduction. Mesh will frequently appear, especially in mechanical problems. So you have a bond graph, then, for example, looking something like this. A one junction, and then you branch, having two zeros, and then they are joined again to another one junction, and then continue. From this 0, you will then have out two other elements. As a generic element, the book uses Z, Z1, Z2. Something like this. It's possible with such a mesh to go through the whole story with causality, strokes, finding the state equations. Yes, it's possible, but rather tricky, rather messy. So what we are going to do now is change this bond graph to something without this circle, without the mesh, as we call it. How to do that? Well, I here have two zeros. Two common efforts. So this one is effort 1, this one is effort number 2. Okay? Then for all these bonds, the effort here is 1, effort 1, and for these three bonds it's effort number 2. So here I have effort 1 and effort 2, right? Must be. What do I have here then? Well, that must then be the sum of them. So here I send in effort 1 plus effort 2. That has to be the case. F at 1 here, F at 2 here. What do I get on the other side? Well, here I have F at 1 and here I have F at 2. And then the summation rule around the one junction dictates I get back F at 1 plus F at 2 on the other side. So the effort goes straight through the entire mesh. Aha. Then I can replace everything with something like this. I use a zero junction because I know the mesh, the effort is equal on each side of the mesh. But I have two elements here, Z1 and Z2. They don't have to be just one single element. They could be big, complex bond graph, of course. So, but look at them just as something, some one or more elements. So we still need a one junction to branch the flow. So I will have to do something like this to find Z1 and Z2, like that. So yes, you have common effort, but around this one junction, the effort will branch into each of the two elements, as they should. And that is identical. That's exactly the same. Any questions to that one? So this structure, much easier to handle. Absolutely. Let's take the other one before we look at an example. So the other mesh, you just switch the zeros and ones. Now we have a 0, branch to a 1, 1, and join together to another 0 and continue. From these ones we have Z1, Z2. So now the philosophy will sort of be the same, but now we look at the flow. The one junction up here has a common flow, Q dot 1. This one, Q dot number 2. What's the flow here then? Well, that's a common effort, so we have to sum the flows around the zero junction. And out we have Q1 plus Q2, which must be the same as goes in, Q dot 1 plus Q dot 2. Which is exactly what we find on the other side. Q dot 1 plus Q dot 2. So the flow goes straight through the mesh. Same flow on each side. Then I can replace the entire mesh using one junction. The flow goes straight through. So that will be the philosophy. But of course, you have to branch the effort into Z1 and Z2. So you're going to need a 0 to make the branch here, like that. So that's the two types of mesh that we can reduce. You have more advanced meshes as well, but we won't bother ourselves with that. This is as far as we go. Any questions to that one? That's okay. That is good. Let's find a nasty example here. Here we have one. That's actually problem 5.1, I think. So we have a force acting on a mass here. So this mass number 1, he has a spring and a damper in parallel before we hit another mass, 2, and he has one spring into a solid wall. Here we have it. Make a bone graph of that one. Okie doke. Mechanical problems start with identifying elements, plates, couplings that has its own velocities. So clearly this mass number 1, he will be represented with a 1 node, has his own velocity. He has mass, so inertance number 1. He's attacked by a force, so I'll have the effort source hitting him. Okay, to the right of this mass you have 2 bonds and a spring and a damper. Both will now be inserted with a zero junction, same force on each side. So here C1, and down here to a resistance. Then we are joining these two together in another 1 junction where I have a mass number 2. Continuing, I have another spring inserted with a 0, spring number 2, and finally 1 junction where the velocity is 0. There I have my raw bond graph. And of course the last one there we can skip. No velocity, 0 power on this bond. Okay, then also we can skip this is 0, can remove him. And then we can't really do anything else, can we? Except we have been taught about mesh reduction. Yes, we have a mesh here. Yes, we have a mesh. That was the first one. 1 on each side and then zeros up here. So yes, here we can use the mesh reduction, but we can't use it directly because for this first 1 junction here, he should have 1 bond hitting him and then the 2 bonds hitting the zeros, not with an additional mass, not with an additional bond. And the same goes on the other side. We mustn't have this bond present. So how should we think here? Well, rewrite the bond graph as follows. You have a 1 junction and mass number 1. Then you insert an additional 1 junction. Nothing wrong with that. And then you branch to each zeros. And up here we had C1, down here we had resistance, joining them in a 1 junction, and again insert another 1 junction where the mass 2 can be inserted, and then finally the spring 2 as well. There you have it. Now you have a pure mesh in the form that we sort of demands it before we can do the mesh reduction. So what will the bond graph be? Remove this one. Any questions so far? It's okay? Inserting a 1 next to a 1, I mean, it doesn't change anything. So normally here we would just join them when you have 2 similar junctions next to each other. But here I inserted 1 just to have the mesh pure and nice before I do this mesh reduction. So now let's see. Effort source hitting a 1 junction, I1. And then we had the mesh reduction. What did it look like? It looked like a 0. And from this 0, we go up to 1 junction where we branch now to find C1. And on the other, find R. I cheat. I do it like that. Then we can remove this. And then continuing, we have a one junction up to mass number 2 and C2. There you have the final bond graph. Much easier than to annotate, find the equations. Is it causal? Shall we check? Because this will now be the start of chapter 6, causality. Is this a causal bond graph? Let's try. You always start with the sources. Always start with the sources. Effort source, it's the effort that goes into the system, hence the stroke must be like this. This doesn't dictate anything for this one junction, so what do? Well, I have plenty of I and C elements left here, so we just gonna start by choosing the integral causal form. And for mass it should be like this. Okay, then I have found the one and only stroke away from this one junction, then he dictates the bond has to be here. Continuing, this 0, well, he should have one and only one towards him, so this doesn't dictate anything. Let us take the other mass as well then. I put a stroke here. That's what he likes, integral form. Then I have found the one and only away from this one junction. Then the two other has to be like this. This is very nice for this C2 element. It's also an integral form. We like it. Now for this 0, he has both bonds here away from him. Then it has to be towards him here. And what about this final one junction? Yes, we have found the one and only away from him. Then the two final bonds has to be like this. And it turns out then also for the last spring, yes, it's a causal system. So here, if you want to do the programming, you will have to then deal with 4 first-order differential equations. You have 4 energy storage elements on the integral form. Any questions to that one? I won't bother finding the equations. You can do that in the break, right? I think it has a solution as well if you want to have a look at it. Yeah, some page somewhere. Now, jumping into chapter 6. You have the recipe immediately. Apply the mandatory causal strokes for each effort and flow source. You start with the sources. But it has to be either an effort source or a flow source. If it's a real source, what do? You go home and take a beer. You can't do it. Except maybe you could then use the equivalence sources that we learned yesterday, Norton or Thevenin equivalence. Then you are good to go. But if not, then you can't use causality at all if it's a real source. Start with the sources, and then point 2, as soon as you have done something, a stroke, see that if you have any other mandatory strokes dictated by zeros and one junctions, or transformers, gyrators. If not, and continuing, choose the integral causality for any I and C elements you have left. And as soon as you have taken a choice there on an I or a C element, go back to point 2. Do you have any other mandatory strokes now? And so you continue. So this is the work stencil, you might say. The work procedure for causal strokes. causal stroke procedure. That is 4 steps. When you have done this for a bond graph, you have 3 possible outcomes. 3 possible outcome. Possible one, it's a causal system. That means all bonds has causal stroke, and all IC are on integral form. And that is what we have seen so far. But we have other possibilities as well. Something called an over-causal system. Over-causal, all bonds have got the strokes, but some, meaning one or more, IC differential form. So you try to choose integral form as long as possible, but all of a sudden the rules then dictate, the 0 or 1 junction dictates some of these will be on a differential form. And finally the last one. Now we have causal, we have over causal, and of course the last one then is called under causal. And the under causal, maybe a little bit more rare case, but it happens sometimes. You have some bonds has not received a stroke. Some bonds without stroke. Some bonds without a stroke. How can that happen? Well, remember your choices. First of all, the sources, you have no choice at all. They are given. The only choices that we can do are if you have any compliance or inertance elements. Then you can choose the integral causal form, like this for a C, and like this with an inertance. So you choose that as long as possible. But if you have too few of these, and you have plenty of these resistances, for a resistance you are not allowed to choose. So don't try to think, don't try to grow a brain. That's not a good. Leave the brain home when you do these bond graphs. It's sort of you do it sort of without thinking actually. So you're not allowed to choose on a if you only have resistances. Then it will mean your system then is under causal. And how to handle that one we will see shortly. But these are the outcome. Over causal, this will happen frequently. Under causal, well, it may happen. Not so often, but it will happen. That was the theory. Questions? That's okay. Let's see, we have Yeah. Yeah, here you have the possible outcomes. So the pure causal bond graphs, they are actually quite straightforward to handle, not a problem. And the state equations should be readily found. Now we will jump to a over-causal example. Now, before we do that, let's just have a look at the forms that we are searching for. Integral form. You have the C element, and then you want it like this, and you have the inertance like this. When this happens, you immediately write Q dot and Q over C. And here you write P dot circle P over I. Circle meaning you will obtain one differential equations from each of these circles. So here you will write the effort equals, here you will write the flow equals. So here, these are the linear sort of definitions of a spring and an inertance. If they are nonlinear, then you will have it a little bit worse. This effort here will now be written as an integral of Q dot divided by C with respect to time. And here the flow will now be time integral of P dot divided by I dt, if they are nonlinear. If C, I nonlinear. So there, of course, you can have a tough job doing the integral. Depends on how complex these functions are. Linear, no big deal. Then it's straightforward. What then happens when they turn out to be on a differential form? Differential form. Then we have the C causality like this, inertance causality like this. This is what we don't like, but of course, yes, we can handle this one. So here it was sort of the flow and the effort, very nice coupled. What do you have here? Well, now you have the stroke towards the spring element, hence it's the effort that goes through the causal stroke. And what do you get on the other side? Well, if you are in doubt, look at the definition. This effort, that is Q over C. How to construct a Q dot out of this one? Well, you multiply with C and take the time derivative. So here you will have d dt of this effort, whatever you have here, multiplied with the C. Sort of thinking backwards, you might say. For the inertance, there we have the flow sort of attacking the symbol, the inertance. So here we start with the flow. Start with the flow. What do we get on the other side then? Well, again, have a look at the definition. The flow can be expressed as P over I. This is what we start with. How to find the P dot? Well, you multiply with an I and take the time derivative. So d dt of the flow multiplied with di. So that is actually all there is to it. And with an over-causal bond graph, we will then experience one of these, one or both. So this is how we then must handle it, using these derivatives instead of the nice P dot Q dot form. Okay, any questions to that one? No? Okay, we will then start next lecture with an example and see how this is done. And we stop here.